In a spectroscopy experiment, like infrared spectroscopy or Raman spectroscopy, atoms and molecules are exposed to electromagnetic radiation. When this occurs, we observe that the atoms and the molecules will absorb electromagnetic radiation at very discrete frequencies or wave numbers. For example, on this figure, it's a very complicated figure, but essentially what we're looking at is the infrared spectroscopy spectrum for a hydrogen bromide. And we see that in the spectrum, we don't get a sort of continuous curve. Rather, we get very discrete peaks that appear here. Now, this sort of figure here is very complicated, so I don't want to spend too much detail on it. But essentially, what it's telling us is that for these different peaks at different frequencies, what they correspond to are different energy states. And so the atoms or the molecules for this peak are excited or exist in this sort of energy level, while the atoms or molecules that correspond to this peak go to a different energy level. And so essentially what I'm saying here is that the discrete frequencies observed in a spectroscopy experiment when an atom or a molecule are exposed to electromagnetic radiation, what they essentially serve as evidence of is that they demonstrate that the energies of an atom or a molecule have discrete spacings. Right? And essentially the reason for that is because energy levels for an atom or a molecule have a hierarchy. Right? And these different energies, they represent different sort of mechanisms or movement modes in an atom. Right? And so these different energy levels represent things like the translation of molecules, so moving from point A to point B. They represent the energy associated with the rotation of molecules or atoms, the vibrations, and even, excitations regarding the electrons in the atom or molecule. Okay? Right? And these energy levels, they're not just uniformly spaced out, but you could see here they actually have very different spacings as well. Right? And so at a given temperature, the number of particles that exist in one energy level will be different than the number of particles that exist in a different energy level. And essentially what we'll have is a population distribution of particles in different energy levels. What's important is that the particle or the population distribution we have, that is going to depend on the temperature of the system. And we could change that distribution by changing the temperature of the system. And so in this module, what we're going to focus on is we're going to focus on developing the mathematical or analytical tools that will allow us to describe, the behavior of particles at different energy levels. Or essentially what we're going to do, so in this module, we will develop the analytical tools to describe the behavior of simple molecules in the gas phase.